I give you Dan Kaminsky and the Black Ops of tcpip 2011. Take it away, Dan.
Hey, so who here is excited to hear about DNS? I was gonna say me neither. Yeah, so I've been spending the last couple of months dealing with SOPA. You know what I'm not gonna talk about now? SOPA, because damn it, no. You can go listen to like other people talk about that. Tomorrow there's a really important talk. I think it is. It's by Peter Eckersley from the EFF. He's talking about a proposal called, Thursday, excuse me. Talking about sovereign keys, it's some DNSSEC stuff. He's wrong. But he's wrong in really important and intelligent ways. I'm just gonna tell you straight out, it's probably one of the more important talks that's been here, so I recommend everyone actually goes. This is not one of the most important talks here. This is one of the least important talks here. You know, I've talked about some of this stuff before, but if you're in the room and you're here, you probably haven't heard it, so it's new to you. I'm just here to talk about some toys, some things I've been playing with, some things that turned out to be kind of interesting and amusing. It's sort of a return to form. You know, as a community, we've stopped really looking at network security, you know, mapping networks, evading firewalls, subverting design assumptions. You know, this is probably the right thing to do, because the old net security tricks, this is not how things get broken into. I swear to God, hacking stuff is like comedy, and you tell the same joke over and over again, right? It's like, I got my beachhead. I did my stupid little SQL injection, or, you know, I popped some client always with Java, because it's always freaking Java. Now I'm in one box, and I just go ahead and take the credentials and go next to next to next. And it's the same game over and over. Maybe someday in my career I'll get to break things in a new way. So, you know, network security is only so relevant in such an environment, but you know what it is? Well, it's fun, so I'm gonna go ahead and look at that. Awesome. Let's talk about Bitcoin. Bitcoin was a lot more exciting a little while ago. It's gotten a little bit of attention recently because it turns out to be one of the most reliable, least expensive ways to move money across international borders. This is not because Bitcoin is excellent, it's because everything else is now crap. So, you know, the joke about Bitcoin is that it converts nerd forums into libertarian forums. It's infected everything else in nerddom, so I might as well get into my research. What is it? Kind of an attempt at making a digital currency with no central bank. System with economic properties. I don't know anything about it. I'm not an economist. But to be fair, neither are most economists. No, really. I'll see your propaganda and recognize it as such. Bitcoin is an overlay network. It's an overlay network upon the internet that people think has certain properties. And that's interesting because overlay networks are things I can speak about. Bitcoin in a nutshell does three things, and it kind of does them in a loop. First of all, it transfers money. I, Alice, give Bob 2.1 Bitcoins. So that means Alice is signing a declaration of some transfer with Alice's public key. Then that information is spread all over the world in phase two, which is gossip. Hey everyone, did you hear that Alice gave Bob 2.1 Bitcoins? And that information is transferred around in this big peer-to-peer network as a emulated broadcast. The internet does not really support broadcasting or multicasting because that would require routers to have good code, and no. Yeah, you know why we talk about the network being dumb? Because we saw what happened when it tried to be smart. There's like 5 people in the room who really understand this is the most true thing they've heard all con. The third thing that Bitcoin does is it appends. And this is complicated. Everyone, the official registry of transactions should now include Alice paying Bob, and Bob paying David, and Charlie paying David, and so on. Now, this official log of transaction, this is gossip as well. And what it does is it requires solving a problem. Now, you might remember from school, from classes, you might have math problems in the beginning. They were really easy, and later on, they got more and more difficult. Well, it turns out with cryptography, we can make problems arbitrarily easy or arbitrarily difficult. So what Bitcoin does is it keeps making problems harder and harder and harder until it takes the entire world trying, or at least the entire population, 10 minutes of effort before someone actually comes up with an answer. How do you know that you haven't made it hard enough? Well, an answer comes too fast. You go, oh, okay, I'll go make that harder. This is a really interesting property. It's kind of as if the more gold you mined, the harder it became for gold to actually be found anywhere. So that's kind of cool. And if when you go ahead and you actually are the one who wins this cryptographic lottery, you get 50 Bitcoins, which then you return to the beginning and transfer it, which gets gossiped, which then gets included in the next log. It's a virtuous circle. The crazy thing is it actually kind of works. This is not my Bitcoin talk. I got like a bigger one. It's on dankaminsky.com. What's interesting is that it is not a complete disaster. I mean, come on, how used to it? Look, guys, this is a piece of software. It listens on the open internet. It's written in a non-memory safe language, and if you own it, you get all the money. This should have died immediately. But what's really crazy is when you actually dive into the thing, first of all, ignore all the friggin' specs and documentation, and again, that's a freaking lie. No, this is one of the few things, if you don't read the code to Bitcoin, you have no freaking clue how it works, because they have not even bothered to update their specifications in ages. What's really cool, and this is why a re-implementation of Bitcoin is actually a disaster, because huge amounts of the security model are represented with lines of code that are just missing. Like, you get to the point the bug's supposed to be there, and it's just not there. They didn't even put a comment in. You're like, yeah, but. Thought it was just me. I'm like, man, am I losing it? And then I go ahead and I talk to a friend of mine. He's like, no, my list of 15 bugs is supposed to have, it didn't work either. So, like, what you actually end up finding in Bitcoin auditing is like, they basically got all the bugs that were not totally fundamental to the design. The main bugs of Bitcoin is that it does not scale at all, and it is absolutely not anonymous. Now, what do I mean by not scaling? Don't look at me, just go to their own wiki. They're like, well, if you assume Visa's rates, you're going to have to ship like 60 gigabytes of data in 60 seconds. So just might have to move like a gigabyte of data every second across the entire internet. And that's all. CPU, you're going to have, these pretty huge systems, 50 cores, plus whatever is needed for mining. Storage, I love what they say about storage. They're like, well, 3 terabyte hard drives aren't that expensive. Have you seen what happened in Thailand? You'll only have to buy a hard drive every 21 days. So Bitcoin starts out small, and it ends up with what are called supernodes. A better word for supernodes are banks. Welcome to the new boss, looks suspiciously like the old boss. I'm not saying banks are bad, but like the peer-to-peer model of Bitcoin in the long run is not how the game works. As soon as it gets big, the entire thing switches to a banking model. This actually is not entirely true. I've had some talks with people. The one exception is banks have magic integers that just say how much money they have. Well, that says 1, how about it said 10? They can do that. They can even do that with gold, because no one actually moves gold around. That's a big pain in the butt, unless you're Hugo Chavez. So you just have magic integers that say how much gold you have. And so there's also magic integers. There's no magic integers in Bitcoin. Like, it doesn't matter who you are, even in the supernode bank environment. Yeah, it's actually kind of true. You actually have to have, you have to have generated the keys yourself, or the Bitcoins yourself. And there's just no way to make more than 50 of them every 10 minutes. That's kind of cool. You can't even do that with gold. But, until we get to the point where Bitcoin goes all bank, what can we look at it as? Travis Goodspeed, one of the more interesting characters in the scene, comes up to me and says, hey, Dan, is there any chance we can use Bitcoin as a samizdat service? Anyone here know what samizdat is? It's a way of, transferring information and storing it without, anyone knowing that you're doing it. It's kind of like a under the surface kind of thing. We've always had the ability on the internet to send data anywhere using various cute tricks. But storage has been hard. You can do the old ICMP moon bounce, send a packet to someone, they send it back to you after a few seconds. Some of us would like to store data for longer than a few seconds. That hasn't really been a thing the internet offers. But what about this Bitcoin overlay network? If Bitcoin is eventually going to require a 3 terabyte hard drive every 21 days, and it kind of has to keep that data around forever in order to function, anyone here know Len Sassman? He used to speak here. Incredibly smart cryptographer. Len unfortunately passed away a few months ago. If you go to the Bitcoin database and you run the strings command, now all strings does is say, this is a nice big file you got here. Show me what text is inside. If you run strings on the list of all transactions that have ever happened in Bitcoin, you end up seeing Len was our friend, a brilliant mind, a kind soul and a devious schemer, husband to Meredith, brother to Calvin, son to Jim and Dana Hartshorn, co-author and co-founder in Shmoo, and so much more. We dedicate this silly hack to Len, who would have found it absolutely hilarious. And just because, one piece of ASCII art is not enough, we also put in a ASCII art version of Ben Bernanke, the head of the Federal Reserve, because now Bitcoin depends on Ben Bernanke. And this can never go away, by the way. Like, they gotta cart this thing around like luggage for the rest of Bitcoin's existence. So how this works. In Bitcoin, Alice gives money to Bob by issuing sort of a challenge. Whoever can sign a message with the public key that hashes the following bytes may claim this money. Well, bytes are bytes. Instead of pushing the hash of a public key, which is 20 bytes, we push 20 ASCII characters of a testimonial. Now, this does cost Bitcoin. It costs about 1.0 Bitcoins in total. There are minimums of transferring money. What I did here was actually destroy that money. The network thinks that somewhere, somehow, there must be a public key with a hash of Len was our friend. I am okay with this. This is the equivalent of pouring one out for your homies. Can we get higher bandwidth? Well, Bitcoin does let you send money to a public key directly rather than its hash, so we can go from 20 bytes to 200 bytes. This is not a bug. This is just part of how Bitcoin works. What might be a bug, and they don't think so, they're not going to fix this, Bitcoin allows for a signature, the actual block that says, hey, here's something that I've signed. It allows there to be extra data there above and beyond the signature that makes the information valid. Now, how does this work? Well, it works through the fact that in signatures in Bitcoin, the way it actually says, I've sent money, I, Alice, send this money to Bob, what actually is said is, he who runs this program and satisfies it, they can go ahead and claim that money. So Bitcoin even includes mobile software and still does not die overnight. The way they fixed this problem, because they actually did die one day, they basically said, okay, we have an entire system where you can send small programs around, but we're only going to allow 2 programs. Anything more, anything that does not match our known trusted software does not get to play around. So the program from the receiver is take this signature here and public key and put it on a stack. And the program from the sender is take the signature and public key off the stack and make sure they're good. Now the receiver can put extra stuff on the stack and it just works fine. I mean, look, one side wants a signature and public key. The other side gets a signature and public key. If there's extra, well, Bitcoin doesn't care. So the thing is, we can actually expand these signatures somewhat illicitly. The reason you can do this is because you can't sign yourself. It's a chicken and egg problem, right? You've got a blob of data that's saying everything else is valid. It can't say it itself is valid because it's itself. It's, you can't be self-referential. So when you put extra data into the signature itself, that doesn't matter. The signature is only covering what came before, not what comes after. What is interesting, though, is that when you add data, I told you there are 3 parts of Bitcoin. There's where you transfer information, there's where you tell everyone about all the transfers that you heard about, and then there's this third thing where you say the official register of all transactions that have ever happened. Now, in this third case, where you have the list of all the stuff that has happened, and you're the guy who did all the hard work and did all the mining, you're basically taking a collection of everyone else's transactions, smashing them together, and then putting your stamp on it. It turns out in that last phase, you can throw a bunch of extra crap in, because everyone else's signatures only covers what comes before the signature. You're going ahead and making things official. You can actually throw extra stuff on and then make that extra stuff official too. So it turns out anyone can add additional data to an otherwise valid transaction. It's not that useful. It's not that valuable. This is the kind of bug you find in Bitcoin. Like, this is exciting crap, right? Everyone else is playing with, like, I don't know, buffer overflows and telnet D, and that's exciting, right? This is like the extent you get in Bitcoin. It's like, I can crap a couple extra bytes in. The long and short of it is, this is the best you get. It does actually mean you can build a Bitcoin file system, Travis, but if you really want to go ahead and have like a bunch of data that the world has to cart around forever, Bitcoin will do it for you. Let's talk about anonymity. There's a site called blockexplorer.com. The thing to realize about Bitcoin is there's no magic person who holds the truth. It's not like DNS where there's a single root and then things delegate down from there. Instead, it's like what we would have done pre-DNS, where everyone just passes around the truth, this giant host file. And then there's keys around to try to make it somewhat hard for people to make fake branches. What you actually get is you get this public ledger. This is a list of all transactions that have ever happened in the world. That's what ultimately that big pile of data is that Bitcoin's handing around. So Bitcoin, you'll have a bunch of sources that are giving money to a couple of destinations. All these sources are the same person. One of these sources is the people on the left. So even though they all look like random values, these are all the same guy on the left. And then it includes one of the people on the right. So de-anonymization on the first layer happens just because, you have multiple keys and multiple random identities, but you can see they're like the same guy because they participated in the same transaction. So when you draw these graphs, these guys, Reed and Harrigan, that are out in Dublin, really fun guys, went out and met with them. They actually went ahead and monitored, like, okay, we've got this thief, everyone knows he's a thief, let's go ahead and link him to all his other identities. And then they found that one of the identities, the guy had actually posted on a forum, hey, you should all donate me money, and here's my IP address and information and all that. So they managed to link him. One of the identities was public, and it infected the other 70. So this is kind of how normal Bitcoin de-anonymization works. It's super noisy and deniable, and Reed and Harrigan admit it. Naturally, much of this analysis is circumstantial. We cannot say for sure whether these flows imply a shared agency in both instances. There's always the possibility of drawing false inferences. Well, okay. Is there another source of data? Well, there's the official record of all transactions that goes around the gossip network, but there's something else too. There's the gossips of things that are not official yet. There's just Alice paid Bob. These are called loose transactions. These are basically gossiped around so the next 10-minute interval can collect them. always refer to a single identity. So it's a big relay race. Alice tells Bob and Charlie about a transaction. Bob tells David and Eric. Charlie tells Frank and Gary. The way you attack this is you just connect to every node in the world. And then once you're connected to every node in the world, you see who tells you about a transaction first. And the first person who's in the relay race is not relaying it for someone else. They knew about the transaction because they done the transaction. That's them. So, people say to me, but you couldn't possibly connect to every node on the internet, to which I say, have you seen the size of distributed denial of service attacks? I can just go ahead and send packets to everyone, and they'll go ahead and respond to me. So that's what I went ahead and did. Funny thing, by the way, back in the day, I used to do large-scale internet scans, and I was like, kernels, they're so slow, they have sockets suck, Well, something happened, and it was called the web, and the web made network stacks have to get really, really fast. So now you can go ahead and in Python connect to 30,000 hosts, and it just works faster than if I went ahead and just generated the packets myself. So it's kind of cool. So I wrote some code called Blitcoins, kind of a graphical joke, and it goes ahead and it connects to every node in the Bitcoin network. And then once you do that, whoever tells you about a transaction first is the actual source. So how do you find out who to connect to? Well, you can just scan the internet on 8333 TCP. You can join IRC. Oh my God, IRC never went away. Is it a botnet command and control network, or is it Bitcoin's network? I don't know. They work just the same. So I wrote some code in Perl called bitbot. I'm pretty sure Perl is a language optimized for writing IRC bots. And so once you go, and the third thing you can do is you can just ask every node in the Bitcoin network to tell you about all the other nodes that it knows. And it's an overlay network. It will tell you. Believe me, it will tell you in massive, incredibly deep detail. So going ahead and getting a view of the entire Bitcoin cloud is pretty trivial. When you go ahead and you ask the Bitcoin devs, they basically say, yeah, we don't even try to be anonymous. Anonymity is not a service we offer. This is their position now. Their historical architecture reeks of trying to do anonymity, but here's what happens in development sometimes. You totally fail. Sometimes you try to build a feature, and at the end of the day, you didn't get it. It don't work. And that's kind of what happened with Bitcoin. They obviously tried to go ahead and make this thing anonymous, but they ended up realizing they backed themselves into a design corner. Actually, it turns out a lot of the inefficiency of Bitcoin comes from this half-assed version of anonymity they implement. They'd be a lot more efficient and, frankly, a lot more scalable if they got rid of it entirely. So what about Tor? Well, Tor obfuscates the IP addresses derived from outbound connections. That it does. But it does nothing if you're listening. If you allow inbound connections, people can go ahead and connect to you, and then you'll go ahead and give them whatever, you'll relay your transactions to them directly. So I think we filed a bug in Bitcoin to go ahead and shut off the listener if the outbound was Tor, but I don't know if that actually got merged in. It might have. What about unreachable nodes? Most nodes are behind NAT and only connect via outbound links. The amount of Bitcoin, the size of the Bitcoin node, the size of the Bitcoin network 6 months ago was something like 60 or 70,000 nodes. But only 3,000 to 8,000 of those nodes allowed inbound connections. So if you just create 3,000 to 8,000 nodes yourself, or I don't know, like control some botnet somewhere, you're half the gossip network. Each node in Bitcoin will connect to 7 nodes and for gossiping. So you probably only need like a few hundred to be one of those 7 that are in the first layer that each node goes ahead and makes their outbound connections to. The other thing, and this is where we get to stop talking about Bitcoin. I know some of you are just excited about that. Many users are behind wireless routers. Routers implement NAT. This is where outbound is easy, but inbound is a pain in the ass. It's a poor man's firewall. And don't mock it, because it sure worked a hell of a lot better than the firewalls we actually did have in 2001. And some that we have in 2011, frankly. Most home routers implement UPnP. It's called Universal Plug and Play. UPnP allows nodes inside your network to allow your router to open up ports from the internet. Bitcoin will actually, by default now, tell the router, please open up my UPnP ports. But what if someone's running an old client that didn't actually go ahead and ask for the ports to open up? Well, how UPnP is supposed to work is that internal hosts will send out a multicast message out by SSDP. Multicast works fine on like a single network. It's just when it tries to hop over like anything larger than one LAN that it becomes a disaster. What's supposed to happen is that whoever on the LAN that actually does support UPnP via this SSDP protocol, whoever actually supports it is supposed to reply. And the reply is supposed to contain some secret information. And then that secret information is then unicasted towards towards the UPnP port or UPnP service. And now you can go ahead and make requests. So effectively, it's a challenge. The server wants to know the client can actually hear it, that it is actually on the LAN, that it is actually local. UPnP is supposed to only work on internal interfaces. It'd be tragic if routers listened to the internet and said, hey, internet, you want me to open up any ports? Yeah. Turns out that a bunch of routers not only listen on both internal and external interfaces, but they don't actually have the randomization, so anyone can ask them to do anything. This sucks. And by the way, this is not a thing that is like dotted around. Entire countries have like a single ISP, and that ISP has like a single wireless node that they give to all their customers, and that wireless node implements UPnP with no randomization and outbound listening. So, yikes. Now, I want to be clear, not everything on the internet listening on 2869 is fully open. Everyone gives Microsoft crap, but all the Microsoft listeners are actually fine. They went ahead and implemented randomized endpoints. So yeah, you can talk to it over TCP, but when you actually say, hey, you open up some stuff, it goes, you don't have the secret that I would have given you over the LAN, screw off. Right answer. But a huge number of nodes are hundreds of thousands to millions. You can just hop on the LAN by asking their router on the external interface to let you play. I'm not the first to start playing with UPnP. It turns out there's like a small research community that's been looking in this. Go look up the work of a Daniel Garcia, Armin Hemmel, upnphacks.org. People have been poking at this for a couple of years now, and probably by the next DEF CON, we'll have some really concrete data and tools. There's some really nice tools out already. UMAP, that's Daniel Garcia's tool. It's beautiful. Way nicer than the grab I was working on. What about outside the consumer space? Corporate environments are less about Bitcoin and UPnP, more about web services and ACLs, access control lists. Are there ways past corporate ACLs? Well, basically what an access control list says is, if you want to go ahead and talk to this destination, your source must be this particular IP. It's completely stateless. Now, of course, you can just go ahead and spoof your source IP, right? Just pretend to be some source IP vaguely near the target, and you're almost certainly going to bypass the access control lists. Now, I tell this to networking guys, and they're like, but best practices, BCPs, they say that you can't spoof your traffic. And it's like, yeah, I can't spoof my traffic from my little home cable modem provider. From, any real-world hosting, spoofing works fine. People are like, but ISPs should implement. And then you go to and you say, hey, how good's your URPF implementation? Does anyone in this room actually work with a thing called URPF? Anyone? One person. As someone I don't even know. Raise your hand if you think it's a complete piece of crap. Right? There we go. I just got a thumbs up. Know the guy. URPF scales right to the point that it works for a single network and a single cable modem or DSL. URPF is supposed to automate a network knowing which networks it's supposed to be able to send traffic as. And it don't work. It really doesn't. There's no way you can piss off a network engineer more than being a security guy saying, your security technology doesn't work, network guy. Gotten in horrible fights that way. What can I say? It doesn't work. So, is IP spoofing still effective? Well, this is an old trick. I said I was going to talk about DNS, but this is just fun, right? So what you do is you go ahead and you generate a query for some random domain, subdomain under a domain that you control. You craft requests for that randomized domain all over the internet from people's neighboring IPs. Now what happens is this goes through the access control lists and it arrives at the name server. Name server is like, oh look, I've got a request. Now it won't send the reply back to you because you spoofed your source, but you control the domain. And so when this random name server that's, every network's got a name server, when this random name server sees your request, it has to forward the request back to you. So now you go ahead and okay, if I spoof traffic with this source IP to this network, I actually do see a request, so I know I can get in. Now this only works for obscure application like DNS and UDP. Certainly nothing like TCP, right? All right, so let's talk about some wonky stuff. Most modern protocols run over TCP. This is a reliable communication protocol. Some of you in the room totally know about it, some of you don't. So let's do some basic introductions. Alice sends Bob a SYN, contains a random sequence number. Bob replies with a SYN-ACK containing both Alice's sequence number, proving that Bob could hear Alice, and then his own sequence number. Alice receives the SYN-ACK, sends an ACK with basically showing that she got Bob's number and that she's still Alice because she knows her number. So the security model as what it is that you know that you're speaking to someone who can actually hear you because they saw your sequence number, you saw their sequence number. So sequence numbers become kind of a form of a really crappy password. They weren't intended to be this, right? They were just intended to make sure that you knew where in a byte stream you were and that the two sides had a similar idea of what was being sent. But we turned them into kind of randomized passwords. Here's the problem. Connections are identified by a combination of 4 values: source port, destination port, source IP, destination IP. Sometimes connections are recycled. So you'll actually have this what's called 4-tuple used once over again. So just an example, and this is a DNS request, 24.123 from a random source of 50,000, talk to 4221 on a totally non-random destination of 53. The most dangerous thing that can happen to TCP is that packets from a new connection look like they're packets from an old connection, because everything built on top of TCP assumes reliability. It assumes that whatever it's handed, doesn't matter the noise, doesn't matter corruption, the other guy sent this. There was no screw-ups. There's no error tolerance in anything depending on TCP. If there's recycling of connections, if there's recycling in these 4 tuples, it is possible that bytes from old will appear new. And the way that is fixed, the way you prevent that from happening, is making sure that sequences are as far away from each other as possible. So in other words, yeah, our 4-tuple might be the same, but that old session is sending byte, 1 million. And we're on byte like 3 billion. So these are different sessions. I can drop the packets, no corruption occurs. This is super easy when you have predictable sequence number generation. You just always go ahead and make sure sequence numbers are constantly increasing from session to session to session. But if we're making them random because we want randomized passwords, now we're screwed. Because here's the thing. If you randomly select ranges, I'm getting a little wonky. Maybe go over in time a bit, but check it out. Their sequence numbers are in a 32-bit range. This means there's 4 billion possible numbers. However, you're sending data, right? You've got lots of data in flight. You might have, hundreds of thousands of bytes, which, anywhere in there is valid. Look at it like I've got a little window inside the new session, a little window inside the old session. It's not 1 byte. It's like a range of possibly hundreds of thousands. Got to make sure like this range does not overlap with that range, because if they ever overlap, it's the end of the world. Or you get bad data from an old session in a new one. So what they did is they said, okay, we'll make it so we will be totally random on sequence numbers unless these 4 values are exactly the same. If these 4 are the same and we have a chance of a collision, now we're not going to go random anymore. We're going to go sequential. Sequential from a random offset, but we're going to make sure that it's not like, the random stuff could show up anywhere. We're going to make sure like this session from over here is as far away from this session from over here. So let me give you an example. This is what's specified in RFC 1948. You have some function that takes source IP, dest IP, source port, dest port, and a secret. And then it adds time. The function in this case was MD5. So I have source of 1234 to 2345, port of 50,000 to 80, secret of ABCD. 1234, 1234, time equals 1111. Sequence number is going to be 1234, 2345. I go ahead and I change the destination IP just a little, set that from 5 to 6. All of a sudden, I'm in a completely different portion of the sequence space. Let's move to 89992121. Go back to the original, and that all goes away. It is made guaranteed sequential, so it's back to the original time. Problem. What if someone just floods? The game is making sure it's always increased. The last thing it got more, it could have gone less. It could have gone anywhere. You want to make it so it's monotonic in time. That's the technical term. Now there's a problem, and the problem is memory. Now, what if someone just floods us with connection attempts? They don't need to remember all of our little passwords. They don't even need to use their own IP addresses. We need to remember all of the sequence numbers that they used. This is what's called a SYN flood, and it's old as dirt. So the solution to preventing SYN floods, with this new security model where each connection has a password, it's called SYN cookies. It was specified, if not invented, by Dan Bernstein in '99, finally on by default in Linux in 2008, by coincidence. The password turns into a challenge. If you can send this back to me, I will accept your data. It uses 3/4 the sequence number, 24 bits, to store the hash of a secret, and the 4 tuple. And then 5 bits for time and 3 bits for some random connection metadata. Like, how many bytes, it's called the MSS. How much data can I implement on this TCP session? 5 bits are exposed publicly. 3 of the bits don't matter. So there's 24 bits of security. Well, 2 to the 24 is 16 million. That means to bypass SYN cookies, meaning you're just going to go and say, I don't know what my password is going to be, but I'm just going to try all of them. Trying all of them takes 8 million packets. And it may actually be even less. Now, Dan Bernstein knew this, said no matter what function is used, the attacker will succeed in a connection forgery after millions of random ACK packets. What has changed from 1999 to 2011 is sending 8 million packets is not that big a deal. We have the bandwidth. So what this means is if you've got some web service that's behind a access control list and says, oh, well, I only accept my web requests from like neighboring IPs, people can just send 8 million and get through your crappy little 1999 firewall rule, no problem. So those spoof packets can go ahead and contain, arbitrary web services payloads, and they'll work. I think you actually need to send 2 packets. You need to spoof a SYN, and then you need to spoof an ACK as if you saw what the other side had SYN-ACKed. But yeah, getting through a firewall that is just looking at your source IP, you can go ahead and drop arbitrary web services payloads. And you can know that a spoof will work because you can use DNS to find out that that particular network cares about your spoofed source. So that's what I've been trying to explain if you were wondering where I was going with this. So it gets worse. Are you safe if you disable SYN cookies? Well, not on Linux. Linux is RFC compliant. Actually, now it's safe. They went ahead and actually fixed all this code a few months ago. Let me tell you, no one better in the world to report bugs to than Linus Torvalds. You're like, hey dude, I'm just giving you a heads up. You might want to fix this in a few months. It's like, what do you mean few months? I want to fix this now. Who the hell are you in security? Tell me I have to wait 5 months to fix my bug. I want to fix that in 5 days. Like, dude, don't let me stop you. I was just giving you a heads up. Turns out it took a while for them to actually fix it, and that's fine because it was a complicated bug to fix. So in the, up until recently, Linux went ahead and was compliant with RFC 1948 for the lower 24 bits of the sequence number. The high 8 bits were sequential. So I don't know how we didn't notice. I mean, it really shows up in like a raw packet dump, but it turns out in TCP dump, it goes ahead and, T-Shark, it would actually make all the sequence numbers relative. So it was hiding the fact that they were all the same. So what this means is that you go ahead, from your own IP, you send a couple of queries, you find out what the high 8 bits are, and then now that you know what the high 8 bits are, you only have to brute force the lower 24. You spoof your SYN, you spoof your payload containing ACK. After 8 million tries, you win, even with or SYN cookies disabled. There's some impact on some other attacks. I think in 2005, Tony Watson wrote a really cool paper called Slipping in the Window. He noticed that, so when you're actually sending data in a session, there's one set of rules, but it's a much more relaxed set of rules for resets when you're actually trying to close one. And what Tony found is if you just got a reset in the window, you could, what's it called? Oh, you could shut down connections even with much greater ease. So in a window, TCP, you're sending lots of bytes. You're not just sending 1 byte at a time. So you might have, say, 64,000 bytes. Anywhere in that region is good. If you got to shut down anywhere in there, it would shut everything down. Well, now the fact that in Linux, the high 8 bits are remotely visible, you have an even better view of where you should go ahead and send your resets. Because you're not guessing across 4 billion, you're guessing across, at best, 16 million. And I think the math ended up working. Oh, the other thing is, we've implemented something called window scaling. So in the original design of TCP, it said, well, you might have like 64 kilobytes that are that have not been accepted yet, that haven't been acknowledged. That's the word I'm looking for. So we'll go ahead and send data, even though you haven't acknowledged it yet, up to 65,000 bytes, or 64,000. At which point we'll stop until you say, yeah, I got it. Well, turns out we have these what are called long fat networks. These long fat networks like satellite links and even just really high bandwidth links. You might actually have hundreds of kilobytes, maybe even megabytes that are just in space. They're just floating. And so if you want to really use all the available bandwidth, you have to allow more and more and more data to be unacknowledged. And so you get the window scaled past 64 kilobytes up to possibly megabytes. Well, since there's a bigger window, you end up with, we started out with 32 bits, we subtracted 16 because of the window size, we subtracted 8 because of the higher bits. You end up in an average of like 128 packets to kill a session. Now if you go ahead and make window scaling even bigger, you can get to the point where like a single packet will kill an arbitrary connection without you having any visibility into the data on that session. So that kind of sucks. Is there a possibility of injection? Maybe. The reset handlers only check one of the sequence numbers. There are 2 in every packet. There's the one from Alice, there's the one from Bob. ACK handlers, though, go ahead and check both. So we have 32 bits, or 64 bits, but now we go ahead and we shave off 16 from Alice's window and 16 from Bob's window, so now we're down to 32 bits. That still requires 2 billion packets for a 50% chance of injection. But we have window scaling. Let's say we have 5 bits on each side. So 5 bits from Alice's window scaling, 5 bits from Bob's window scaling. Now we're down to 22 bits. Now we have 1 million packets for a 50% chance of injecting into a session blindly. Now we have the predictable high bits too. So we have 8 bits from Alice's predictable high, 8 bits from Bob's predictable high, 6 bits left. That means 16 packets for a 50% chance of spoofing blindly into a session. Moral of the story, please now have firewalls more advanced than we stop IP spoofing. So that's probably the most obscure thing that I'll talk about. That's a lie. There is some difficulty with ports. Linux has some stuff where it randomizes the source port of a new connection by default. So you do get port ranges that you have to go ahead and brute force, but at the worst case, they end up increasing the amount that you have. Oh, here's the nice thing. Firewalls will not only go ahead and be configured to just block IP spoofing, sometimes they'll take your nice port randomization and make your ports sequential. This was a huge problem with the DNS fix because we were randomizing our packets, but the firewalls were resequentializing them. But even when that happens, even if they're not doing that, you get to 250,000 packets for a spoof. So this is old code. It actually predated Linux's Linus Torvalds access to a source tree, so it was there when it got into JIT. They did actually implement the fix, and it's fine. It raises it from like 24 bits of security to 31 bits of security, and they fixed a bunch of other stuff. Kind of a digression. RFC 1948 is an interesting construction. It involves sequential, and it means that data is sequential and ordered with the key. So if you know all the secrets, everything's in nice order. If you don't know the secrets, it's random and unpredictable. So is this kind of like public or private cryptography with nothing but a password? I mean, that's not supposed to be possible. I guess it's only here because we're at an intersection of network security and cryptography. I had a bad idea. I mean, this is truly an awful idea. Passwords are a bad idea. They're constantly being lost and forgotten and stolen. They're responsible for about 50% of compromises. They look like elite speak. What the hell are we doing here? Suppose we ignore all that. Suppose we assume we're stuck with passwords. What can we do? There's an old challenge. How do we use a password to log into a system without that system learning our password? Well, we often say, passwords should be hashed. Anyone who builds a web app that doesn't hash passwords is an idiot. By the way, is it okay if I go over about 10 minutes? I'm going to go over 10 minutes because I'm an asshole. Come on up and tell me if I'm being a really bad person. I won't do it. I won't do it.
You're a bad person, Dan.
How about 5 minutes?
Okay, 5 minutes, and then gives you 5 minutes for questions and insults.
All right. I've been explaining stuff, so I've been going a little. Okay, so check it out, right? Look. You can hash the password in your database all you want. I still owned your web app, and I'm still watching plain text arrive into it. Oh no, my ownership today has to continue for a few days, and I see all your active users. Guys, there's all the challenge response stuff. We challenge you to hash your data against this password properly. So send me your password hashed against this random value. This requires the server to store the plain text password. Otherwise, it can't send you challenges because it doesn't know what to challenge you against. Or, at worst, it has to do a plain text equivalent thing. This is how NTLM works. The most advanced one is we require knowledge of the password to go from a key pair to a shared session secret. This is how Speak works. This is how SRP works. It requires the client and server to run some fairly obscure code. Good luck getting either deployed, and still the bad guy can go ahead and break in and do their offline password computations. That kind of stuff. So here's an interesting thing. Is it possible, not good, but possible, to build a system where a client only remembers the password, but the server stores nothing but a public key, deploys nothing but a standard like SSL client authentication mechanism to make sure the client has a matching private key, which is derived unilaterally from a password? Can we construct cryptographic key pairs out of passwords? Is that possible? I don't know. Let's see. Well, You know what the one bug that all asymmetric crypto systems that do key pairs, you know the one bug they all had, RSA, DSA, or ECC? Well, remember the Debian bug? They all had a random number generator, and the random number generator was busted, and all the ciphers fell over and died. So all asymmetric crypto systems use entropy as follows. You collect some random bits, and then you permute those bits until they meet certain requirements. And then from those permutations, you emit a public-private key pair. So predictable entropy equals predictable key pairs, no matter what the algorithm happens to be. So what if we turn the Debian bug into a feature? Well, we have hash functions, stream ciphers, block ciphers, all of them can construct into each other. We know how to take passwords and construct an everlasting stream of pseudo-random numbers from them. And this is, pseudo-random entropy, predictable entropy. We can even do this in a way that is hard, both in terms of CPU time and memory. It's called scrypt. So what if we do that? What if we have the output of a password-seeded PRNG be the input to an asymmetric key generator? You end up with 2048-bit RSA key pairs that have a trapdoor in the form of a password. This is not theoretical, this is actually implemented. Normal use of SSH keygen, you go ahead and you generate it 3 times, you get 3 different keys. Because SSH keygen is normally going ahead and going to dev random or dev urandom. Well, we're going to go ahead and hook those. So we're going to go ahead and have every time SSH keygen runs, it gets the entropy as generated from the phrase hi grandma, and now we see the actual same SSH key being generated. I call it Fidelius. This is a horribly obscure Harry Potter pun, because Harry Potter, properly understood, is a story about the epic consequences of losing one's password. So what Fidelius does is it hooks dev random, dev urandom, OpenSSL's randomized functions, and a couple other things, and it makes normally high-quality entropy have a backdoor of a password. It works very nicely. Uses scrypt to require 1 second of processing time per attempt, to make brute forcing quite a bit more difficult. So no, you don't get to use GPUs. What Fidelius gives you is generic multi-application support. It turns out that apps have no need to know that they're even being made to generate things predictably. Servers that have certificates have no knowledge that the private key can be reconstructed from a password. One of the things from Bitcoin, you can actually go ahead and have money sent to, a picture of your mom, and a picture of your mom turns out to be the key to claim your money. It's kind of cool. There are some bugs, not just the bugs of like it uses passwords and they're bad, but bugs like it's super fragile. The actual way entropy is used by SSH keygen is not specified or fixed, so you have to keep using SSH keygen. It's also really hard to salt. There are some tricks, but 2 uses of the same password are almost certainly going to lead to the same private key. And that kind of is a bad architectural decision. There are some tricks that you can do, but bug me about them later. So there's one last thing I want to end with. It's kind of a tcpip trick. The actual heart of it was invented here. Actually, it was invented like in the back over there. But I finally got around after a few years to implement it. Anyone here worried about net neutrality? So I am, maybe you're not. I'm not so much worried about networks that are outright blocking traffic. I am worried about networks that subtly slow things down. What I want to say, if you work for an ISP, in the long run, what I'm about to talk about means I hope you like whatever you're doing being public, because it's going to be. If you're proud of it, great. If you're not, you might want to stop. Let's check this out. Here's your standard network topology. Some client, desktop, has a home router, connects to an ISP. The ISP's got a bunch of network links. Those network links talk to Google or Microsoft or Yahoo or wherever. The fear is this. Some magic box has been deployed within the ISP network in front of all the links. The box matches packets to policies and applies different rules to different packets. These policies can be stateless. Do I like this packet? They can be stateful. This packet is part of a flow. Do I like this flow? Now, the policies can be anything, And they can do anything. They can limit bandwidth, they can increase latency, they can even alter content, throw a few advertisements in there. And the reason people are afraid of this is because ISPs are demanding the right to do this. So it's not like something like subtle or anything. How do we find this stuff? Well, like I said, my fear is not that stuff is outright blocked, because blocking is not subtle. I'm worried about stuff like Bing is 50 milliseconds slower than Google. It's totally deniable. I mean, Bing has different servers than Google. Bing has different networks than Google. This might not be because the ISP is doing anything. This might just be because of the rest of the network. So there's plausible deniability. How do we get rid of that? Well, what we need is normalization. If I have some test system, whether the tester is accessing Bing.com or Google.com, the network path should be identical, or at least uncorrelated with whoever this appears to be. We call this uncorrelation normalization. That way, any changes in behavior of quality of service or of content are not because of the path taken, but because of policy, presumably at the ISP. So the really basic way to normalize is just to ask some test server on the internet for the content from Google or the content from Bing. You're talking to the same server, it's over the same network paths, it's just your host header happens to say Bing or Google. Okay, you don't need to write any code for this, just like deploy Squid, because that's what Squid will do. Now, if you get different performance when you're emulating Bing versus when you're emulating Google, you know that the problem is in the ISP. And this will actually detect very nicely HTTP bias policy today. No work required. The problem is that this is really protocol dependent. HTTP can be made to do this at a low work effort, but other protocols require lots of work to implement and emulate. It's because HTTP really wanted to support caching proxies that did interesting things, whereas other protocols have no idea what's going on. And the other problem is that policies can be really specific to IP addresses. You sniff DNS, you figure out which IP addresses need to be slowed down because you don't like them, and then you go ahead and it doesn't matter if you've got hundreds of test servers around the internet, if policies are only applied to IP addresses that are genuinely Bing or genuinely Google. So I have a solution. It's called Neuter. It's the network normalization engine. And the best way I've found to explain Neuter is this. How many of you guys have ever used a VPN? All right, so VPNs make it look like you're on some other network, right? You got some client traffic is sent from the client to a broker, or VPN concentrator as we call it. The IP address, now your IP is the broker's IP, whatever it gives you. So an IP associated with the broker contacts servers who reply to the broker encrypts the traffic back to you. So the ISP doesn't see anything, right? Like it sees an encrypted stream to a VPN concentrator and the VPN concentrator replying back encrypted. So, none of the filters are triggered. Well, that's a problem. That means we don't actually see the behavior of the filter. So here's what I'm thinking. You do a VPN just as normal, but now, when the broker communicates back to the client, that traffic is not encrypted. It's open in the clear. In fact, not only is it not encrypted, it spoofs the source IP of the real Google, of the real Yahoo, of the real whoever you possibly want. It's unencrypted. It's spoofed as if there was no broker. Why do you do this? You want the ISP to see your return traffic because we're trying to trigger the response. We're trying to trigger the policy that would normally apply to just Bing or just Google. We want it to apply to our normalized test server. The policy engine can't tell because we're impersonating the real entities. The traffic took the same path. It came from the same source. Why else would we be seeing different quality of service? Now, of course, anyone here who's a network engineer knows the bug in all of this. The bug is the policy engine in this scenario doesn't see the traffic from the client to the server. That's encrypted like in a VPN. What if the policy said, aha, I am sneaky. I am not going to filter one-way return traffic because that guy's just trying to bust me. This is a very, very interesting idea. It's also a trap. Totally going to have on the 5. It's great. So check it out. We did neuter, now we're going to talk about something called roto-neuter. In normal neuter, we were spoofing the server to the client. In roto-neuter, we're going to spoof the client to the server. So we're going to take 2 network samples. In sample A, we do nothing. Client talks to Google. Real Google, ISP sees the SYN. You get some performance characteristics. In the second model, in sample B, client talks to the real Google by way of the broker. So the ISP sees nothing. Broker goes ahead and talks to Google, and it spoofs the client. It tells Google, oh yeah, you know, that user at that ISP just went ahead and sent you a SYN. Why don't you send him a SYN hack? In fact, why don't you talk to him? So in this case, the ISP does not see the SYN. Both samples have a real set of responses coming from Google, but in only one of those situations is the ISP seeing the SYN from the client. So if there's different performance characteristics, that means that, aha, you just busted them, having their policy engine be sneaky. So it's a damned if you do, damned if you don't. If the ISP applies policies to the half flows, Neuter can differentiate performance of the spoofed half flow from Google from the spoofed half flow from Bing. If the ISP applies policy only to full flows, though, RotoNeuter can differentiate the performance of the full flow to and from the real Google versus a half flow from the real Google. Either way, I'm going to win. So bias policies might as well be transparent because they're certainly not going to be deniable in the long run. Now let's talk about 3 tricks that get really fun. We're taking full flows. Suppose you really do want the ISP to see full bidirectional traffic. The advantage here is all the policies are triggered. Also, your NATs that might be around, they're all opened up. NATs really don't like it when there's unidirectional flows because it breaks their model of how networks function. The problem is if the ISP sees the real client-to-server traffic, you know who else does? Is the real Google. Like, you're trying to spoof stuff, and Google's like, what is this weird-ass network session I'm seeing? And it goes ahead and it replies or interferes or complains, and it's a real problem. So how do we deal with that? Well, strategy 1 of 3 is we have a bad TCP checksum. So client goes ahead and does all the normal trafficking of data through a broker to the real Google, and then Google replies. But then client does something more, which is actually sends a stream to Google. But all the streams to Google have a bad TCP checksum. So the packet leaves the NAT and triggers the NAT rules, and it leaves the policy engine and triggers the policy engine rules, and then it gets all the way to Google, and Google goes like, this is an invalid traffic, abort. And so that works pretty well. Now the policy engine might go ahead and detect things are wrong, or NAT might go ahead and fix the checksums. This doesn't necessarily work. But you can catch 22 on this as well. The next strategy is to use a low TTL. This has everything be valid, but the packet only gets about 5 or 6 hops out of the ISP. In the middle of some sprint link, some data center somewhere, just drops on the floor. Policy here as well could detect a low TTL and not trigger stuff, but again, you get to catch 22 of them. The third one is the fun one. This is my favorite trick in a while. When a TCP stack receives a message that is not actually associated with a real session, it is supposed to send a reset. It's supposed to be like, this is broken, I don't know what's going on, abort. That is what's supposed to happen, but us security people have said, no. Firewalls, if they get anything wrong, they should just drop it on the floor. Perfect, because that's what I want. I need Google to ignore some of my traffic. So here's what I'm gonna do. The client is going to go ahead and complete a 3-way session with the real Google. And then the broker, because it knows the sequence numbers, it knows the passwords, it's going to send a reset. It is going to shut down that connection on the server. Client, now what happens is the client is doing all the normal stuff where it's proxying connections through a broker and whatnot, but it's also sending real traffic to Google. And Google is going to ignore all that stuff because it's seeing all these packets on a session. That thing already got reset. It ignores it. So, client sending packets to a server, server sending packets to a client, everything looks perfect from a policy standpoint. Policy engine is triggered, but it's not talking to Google. It's talking to me. So I just hit my end of time. Bug me for questions. These are the random toys I've been playing with. I really hope you enjoyed them.
Oh, Dan?
Yeah.
Dan, you may have to buy a bunch of people some drinks.
Really?
Yes, because...
What was the bet?
Well, via IRC, a group thinks that, or has thinks that you may have rediscovered something that they discovered in 2007, and your talk doesn't credit them for the Linux sequence number.
I have it was certainly not intentional. Does anyone have the names of the people I may have screwed up crediting? Because, I mean, that's a really big deal.
Yeah, the links are all down here.
So I will apologize profusely in advance. It's
and buy
possible.
everybody Jägermeister.
I will buy drinks, absolutely. Now, here's the thing. They certainly didn't get it fixed. But if I've accidentally recapitulated some research, I apologize. I do everything in my power to find stuff, and I'm happy to buy Jägermeister for all of you. So my apologies.
Thank you very much, Dan. The poppies and flowers will be waiting for you downstairs.